So we're going to look specifically at infinite geometric series. So when we have a common ratio and it's multiplying and the multiplier makes everything smaller and smaller and smaller. So here I start with Tn equals 10. I have the multiplier is 0.8, so I get 8, and then this becomes times 0.8. So in this case, we're looking at cases where the absolute value of r is going to be less than 1. So in this case, let me just write this down. This is where r equals 0.8. So as I keep multiplying, so 6.4 times 0.8, I get 5.125 times 0.8. I get 4.096 times 0.8, 3.2768 times 0.8, 2.62144. And as we increase the number of terms, as Tn gets larger, if the r value is less than 1, it's getting smaller. And what's happening then is eventually these terms that we're adding get smaller and smaller and smaller, and we're getting really, really, really small pieces that we're adding, which then don't affect the sum very much. And because of this will end up converging to some finite sum. If the r value is negative, it doesn't matter because each term still is getting smaller. So here I'm multiplying by negative 0.5. So here r is equal to negative 0.5. So I get negative 1, positive 0.5, negative 0.25, positive 0.125, negative 0.0625. Okay, this becomes positive 0.03125. And this is going to keep on going, and this is again the Tn is getting smaller and smaller and smaller. So Tn is approaching 0, and so that's what's going to happen every time the r value is less than 1. Each term gets smaller. As n goes to infinity, Sn has a limit. And if we just look at the r to the power n portion of it, as n gets really big, any decimal to a really large power ends up equaling 0. And we could test this. We could test this on our calculator. If I use 0.9 to the power 1 million, or let's go 10 billion, my calculator is going to give me a value of 0. Now, it's not exactly 0, but it's getting so close to 0 that my calculator can't tell the difference. So if this portion of my formula tends to 0 as n goes to infinity, we're going to end up with a, it's just going to disappear. It's going to become a times negative 1. And if we rearrange that, if I just flip the denominator around, I can get rid of that negative. I end up with a over 1 minus r. And only for r less than 0, we can just use this for an infinite geometric series. So essentially, now, we don't write this. We usually just write it like this. S is equal to 1 over r, but this implies, this s without an n there, implies s infinity. So s infinity is equal to a over 1 minus r, and that's the formula to calculate s infinity. So this is only for geometric series, so it doesn't work for any other series other than geometric series. But for geometric series, if things get smaller, that each term gets smaller geometrically, it actually means that the terms are getting smaller very quickly, and they're getting smaller fast enough so for there to be a finite sum, even though we are adding an infinite number of numbers. So we have to be able to recognize when we're dealing with an infinite geometric series. So in this case here, this looks like we are multiplying by 1/3. So I'm going to identify my r value. R equals 1/3. That r value is less than 1, so that's good. Each term is getting smaller and smaller and smaller. Well, that means then that this is an infinite geometric series. which means then it must be convergent. Okay? And again, it means that it converges to a finite sum. This one here, my r value, if I divide the consecutive terms, is negative 0.8. Well, again, that is an infinite geometric series where my common ratio is less than 1. So again, this is an infinite geometric series. Now I need to make sure that it is geometric. So again, this is convergent. This is also a geometric series. However, this is a red flag. The r is greater than 1. Therefore, although it's an infinite geometric series, this does not converge to a finite sum, so we call this divergent. Okay, so it's good to start using these proper terms that we use later on. Converging means it converges to a finite sum. Divergent means the sum ends up being infinite. So if I just keep on adding an infinite number of terms that get bigger, my sum is going to be infinite.